Hello everyone. Today I will explain to you the study of an algorithm for efficient urban building energy modeling and simulation. Uh, last years, energy efficient solutions becoming a prior importance for decreasing carbon emissions and increasing user comfort. And 92% of the total population is living in cities in Turkey. And residential areas are responsible total energy demand of 41%. It's a huge number, and it's really crucial to understand the energy demand profiles of the residential buildings. What are the problems for the urban building energy modeling? Urban building energy modeling requires wide range of information for geometric and non-geometric characteristics. That's why it's composed from comprehensive models, and we need too much time and computing power to execute these simulations. And lastly, we realize that in the literature, most of the time occupancy behavior and the occupancy related parameters is ignored, but we say that it could not be ignored because it gives you the reality or real-time solutions for the urban energy modeling. Basically, this study purpose is to put an efficient bottom-up algorithm for urban energy modeling for the residential buildings, which is simulation-based methodology. What are our objectives? These are to propose an UBM AM framework with the parameterization. It's related with the reliability of your solutions or your computing time, and to decrease the total simulation time to apply in all new or retrofit based projects, and to serve as a feedback tool for the retrofit planning time because of the small time, less time we needed to execute these simulations. And lastly, we introduce more parameters related for the occupancy in order to increase the simulation results. Our methodology composed from the 5 steps. Firstly, it starts with the inputs, the introducing the geometrical information for the simulations, then two-phase sampling, which are the firstly solar radiation analysis clustering and the vertical position-based clustering, then model color characterization, and lastly simulation and validation process. Our research selected observed area is in İzmir, in city. It's a big neighborhood in the İzmir, in the center of the city. It's mostly residential buildings, and we generated a filter to divide the residential and non-residential units in that area. All the extra information comes from TÜİK, which is the Turkish National Standard Office, and approximately all buildings are 24 or 21 meters high. Our first clustering method, clustering method is the radiation analysis. We are executing radiation analysis for all buildings in order to divide their radiation analysis results. We are dividing all the buildings in 10 radiation scale based on their results on the vertical surfaces. And secondly, we are putting extra grouping comparing to their vertical positions. For example, as you can see in the figure 3, the top floors, middle floors, and ground floors are divided from each other. And lastly, for this study, we executed 10 radiation scales and 3 different subgroups of the vertical position-based subgroups. Therefore, totally 30 different groups we divided the whole building units. It's a lot. And lastly, we are executing randomly sampling, equal number of random sampling from all these 30 subgroups. In order to validate the algorithm, we executed 5%, 10%, and 20% simulation sample size of the simulations. In the table 1, you can see the parameters of the UBM model. It's directly related with the reliability of the results and the computing time. Our units are divided into two, mixed zone and heating zone. Why we divided these units? Because based on the two statistical data, we realized that just 20% of the buildings consist of cooling system. So we need to divide this. And these two modes are simulated differently in order to increase the efficiency of the simulations. All the thermal standards came from Turkish and İŞERİ standards. And lastly, as we said before, all the internal laws and occupancy and extra information related to the internal rules and occupancy coming from the TÜİK. And the first results are the radiation analysis, because our algorithm starts with the radiation analysis. All samples, all different scenarios consist of this radiation analysis. Based on these radiation analysis, we are executing sampling methodology. As you can see in the table 2, we have divided in 10 different radiation scale and 3 different vertical position based clustering, totally 30 different subgroups. And table 3 explains the heating only unit simulation comparison, which consists on just heating and lighting. And you can see as the sample size increases, the reliability, the accuracy of the results are increasing, both lighting and heating objectives. For the mixed mode, we added extra cooling demand, and the same scenario happens in here. As the sample size increases, obviously the accuracy of the simulations are increasing, but while the sample size increases, the computing time also increases. And we can see this in table 5. You can see the 20% sample size simulation scenarios. It's approximately more than 250 minutes, but just sample size 5% sample size is less than 100 minutes. But all the radiation analysis, the first place radiation analysis for the minutes, is added in the total period of these simulations. And for obviously the vertical position is just functioning based division, so it doesn't require any extra time. And figure 7 is highly important to explain the performance of the model. And you can see that the 5% mixed mode units results, the error ratio is the highest one, because these are the 20% of the total simulations. As we talk about it, just 20% of the buildings consist of the cooling energy demand. And from these 20%, we are selecting just 5%. As you can understand, the sample size is highly low compared to 20% heating only simulation result. They are the lowest ones compared to highest ones. It is directly related with the sample size, but we realize that it's a trade-off actually. What we can see that 10% and 20% results are accurate compared to 5%, but it's a trade-off because the 5% simulation time are the lowest one, less than 100 minutes. It depends on your simulation accuracy expectancy actually, or the time that you have in the first place. And in extra, we would like to add that we are executing these simulations in the urban context, but we didn't add any extra context elements such as cars, parks, trees, in order to focus on the similar radiation methodology, vertical position based clustering, and our efficiency of our algorithm. And lastly, the radiation analysis is inspired the methodology inspired from the Timur Doğan's paper, as we added in the reference page. In the conclusion, we propose the UBM-AM framework with the optimal option of parameterization. It can be used as a feedback tool for the early design or early phase of retrofit planning. It can be just decrease the simulation times. For the 5%, it's about 10 times lower, and for the 20%, it's 5 times lower. And we realize that adding occupancy profiles, occupancy-related parameters, it increases the accuracy of the models. For further work, we are aiming to validate our results with the real pre-collected data, but it's nowadays, currently, it's a bit hard to obtain these data because of the personal data protection law, but we are aiming to execute it in the next study. Thank you for all.